Well, this is our second day on hyperbolas in 8.3, and we're hitting a lot of our objectives here kind of again and again, especially the first three. We've done a lot of this. But the geometry of hyperbolas having subtraction in there is the big deal. And when we get down to understand applications of hyperbolas, we're not necessarily going to do a word problem involving hyperbolas, but we're going to read a little bit about where hyperbolas are used in real life and those types of things. So we are down here where we have this extra example. And this extra example is taking the standard form equation and putting it into the general form that we have that has our h's and k's and a's and b's in it. And on a test or a quiz, they wouldn't tell us it's a hyperbola. We'd have to figure that out. So prove that the graph of the equation is a hyperbola, find its vertices, foci, and asymptotes. And as I take a look at this, I start to think, okay, well, it's got the x squared and the y squared, so I know it can't be a parabola. If it has a y squared and an x squared that are both positive, then it's an ellipse, but it doesn't. It does have subtraction there. And so that puts me into the, hey, now I need to think hyperbola. So seeing that the positive squared term is the y, that's going to come first. And I start thinking, how am I going to take what they've given me and make it look like this? And again, it's the completing the square process that's going to do that for us. But to complete the square, we're going to have the y's grouped together. We're going to have the x's grouped together and see what happens. So let's put our y's together. And move the 63 over to the other side, because again, it wasn't helpful where it was. It's not a perfect square. And we know we have to complete the square to do this anyway. So now, next step would be, you can't complete the square if you have something other than a 1 in front of the squared terms. So we'd factor a 9 out of the first two, and factor a -4 out of the second two. Now we'll complete the square. So we have to remember our little b over 2 squared formula. And I was just thinking when we were going over this first hour, completing the square was one of the really intense parts of the beginning of the year, learning how to do that with all kinds of numbers, and now we're adding a new piece to it. So it's like we're starting and ending the year with that. And our b in this one would be -2. -2 divided by 2 is -1, and when you square it, you're going to be adding 1. But you have to remember you didn't just add 1 over on this side, because it was 9 times 1, which is 9. And then for the second part, I have to complete the square with my -6. -6 divided by 2 is -3, and -3 squared is 9. And we have -4 times 9, which is -36. So we're subtracting 36 from the other side. So now we'll go ahead and write our binomial squared. So y minus 1 times y minus 1 would give us our y squared minus 2y plus 1. And then x minus 3 squared. And do a little bit of math on the other side. 63 plus 9 is 72, and 72 minus 36 just happens to be 36. So we've gone through this process before, and now I'm going to let you help me out a little bit more. So can somebody tell me what we should do next to get this to look like a hyperbola? All of the terms by 36. So far, so good? Okay, Because now what I need you to do is take a peek at this and say, hey, Cedarholm, I know this about it. Tell me something you know about this hyperbola. All kinds of things to choose from. It is vertical. The y squared is positive. Good. Something else that you know. It gotcha. Yeah. That was one of those things that, I warned when we get to the test. Unfortunately, we want to go HK right away, but yep, this is backwards, so good catch, everybody. 3-1. Something else you know. Caroline. I'm going to go ahead and put the plus or minus piece on there. Well, I think we could get a pretty good graph going with that information. That's a good start. So let's go over here and put our center at 3-1. And we have to remember, A is not always the biggest number when you're talking about hyperbolas. So with this one, A is going to go vertically because we saw the y squared first and it's only a 2. So up and down from that center, 2 units. And now before I get too much other stuff on here, the problem did ask me to identify the vertices, the foci, and the asymptotes. So I would probably stop right now before I get too much information on this graph and write those vertices down. And you can either do it mathematically or you can just, hey, I just graphed them, I'll count and find the ordered pairs. But what we're doing here is we're saying that A needs to be used to make it move up and down, which would be the y values. So 1 minus 2 would be -1, so 3, -1, and up to 3, 3. Now, let's get B on there. Again, they don't call them covertices, but we use them as covertices. So 3 units right and left. They also don't ask us to write them down. They had that fancy name semi-conjugate axis for them, but generally with the hyperbolas, they don't have us write those. But we make our little box from them. And put in our asymptotes, because they are certainly a really important part. And again, here's where you have to be careful. You have to remember this one was special because it was vertical. So make sure you're putting your branches up and down. That's another thing that when we can in other years give the tests back, students would get them back and immediately go, oh, I can't believe I did that. I even wrote down it was vertical, but they graphed it right and left. It happens. All right, so we've got it up there. We don't have all the information they wanted, so let's backtrack. They wanted the foci. So in order to find the foci with a hyperbola, do I use the Pythagorean theorem with a plus or a minus in it? Plus, because it already has the subtraction in the formula itself. And we have a squared and b squared right here, 4 and 9. So c equals plus or minus the square root of 13. And we stop and think. Anything I can do with that, simplify it. No, 13's prime. So what I have to know is the foci go on the same axis as the transverse axis, so our vertices. So that means this is still going to affect that 1. We're still talking about up and down for vertical. So the foci will be 3 and then 1 plus or minus the square root of 13. And asymptotes. Which again, don't overthink the asymptotes. Everybody's like, I'm going to flip through my packet and find those formulas. No. Basic rise over run. Go back and look at easiest spot, center to the upper right-hand corner of your box and do rise over run, up 2 and over 3. But then remember, this one wasn't centered at 0, 0. And if it's not centered at 0, 0, we have to show the translation. So the translation is going to be the x minus h, which is our x minus 3 piece, and then plus k, the up and down part, and that was a 1. So again, very visual. I mean, if you can put the visual together and get the graphs, the rest of this is going to come. You don't memorize boxes full of information. That just makes it much more difficult. Let me make sure we did it all. Our proof was algebraic, vertices, foci, asymptotes. We've got it. Now, there's nobody on the Google Meet, but I think I'm going to do this the same way I did first hour so that everybody can get working on the homework when they get to that point. We're going to go ahead and read about the good stuff for hyperbolas. I'm going to hit the lights here, get those up for you. And I do the reading most days. So today I'm going to ask somebody to volunteer to read the first paragraph about Kepler's first law of planetary motion, please. There'll be 2 readings today. Go ahead, Caroline. Good, thank you. So 2 major themes in that paragraph. The first is when you're talking about, and they keep calling them massive bodies, they don't want to call them planets because, as you know, Pluto got dropped within the last 10 years or so. The bigger one ends up being the focal point when you're talking about all of the rotation that's taking place. And secondly, huge Star Trek moment here. Any Trekkies in here? People that watch Star Trek? Love Star Trek? I do. Star Trek, they say, is one of those things where they write about it and then people try to make it come true, and that's why that happens. And in this last piece here, more than once, the Star Trek crew has had to slingshot around the sun to get to where they needed to go and use time travel. So definitely a little information there. And this, I don't know, it might become more relevant in the coming days as, you know, we have all this new information about stuff going on in space. Just yesterday there was another new article about where they keep hearing these repeated sounds from, and that they're trying to track it down and figure out exactly in the solar system where that sound is from. So let's read about the reflective property of a hyperbola. So somebody to volunteer to read about that, please. Come on, you all have to be good readers at this level. The faster somebody reads it, the faster it's over. Go ahead, Tanner.
Like other comets, a hyperbola can be used to make a reflector of sound, light, and other waves. If we rotate a hyperbola in 3-dimensional space about its focal axis, the hyperbola sweeps out a hyperboloidal revolution. If a signal is directed towards a focus of a reflective hyperboloid, the signal reflects off the hyperbolic surface to the other focus. In figure 8.129, is also the focus of a small hyperbolic mirror. The light is then reflected off the hyperbolic mirror toward the hyperboloid's other focus, FH equals FE, which is also the focus of an elliptical mirror. Finally, the light is reflected into the observer's eye, which is at the second focus of the ellipsoid.
Yep. So this is, like I said, in the news now, they're talking a lot about using things like this, hyperbolic reflectors, but mostly for sound. You know, they're interested in catching sounds that are coming from outer space. So who knows, maybe some big-time jobs open up in this field in the next few years. It's one of those unknowns that we have. Now, what we're going to do the rest of the time is I'm going to go ahead and give you the assignment right now, so I'll have you write that down. But we still have a worksheet to do as an activity here in class, because you need more practice at completing the square to get your conics looking good, because I want everybody to do really well on that on the test. But go ahead and write this down, and then if you remembered your worksheet, please get that out. If you didn't, I do have some spares. So for the video, what we're doing the rest of our time together is we are going to be working on the Completing the Square worksheet that is in the black folder on Schoology, and it's labeled with today's date, May 26th. And for the Google Meters, the key to it is also in the worked out solutions. So that will be what we're going to spend the rest of our time doing in class, an activity with this worksheet.